All right, so we'll get started with topic 2. Topic 2 is focused on roots of equations. So what's a root of an equation? So wherever your function intercepts with the x-axis is your root for a specific function. So we can see here, this is a line. It intercepts around negative 0.5. Here, this is another function, and it has two roots in this case. So from calculus, in your previous courses, you've seen that it's quite easy to find the root if you have a quadratic equation, right? Or a polynomial, a second order polynomial, you could use the quadratic equation. Or if you have a linear equation, you can also solve those quite easily. Where numerical methods comes in is when we cannot use these simple methods, right? We have equations that are nonlinear, and we have some examples here that make it difficult to find the roots. So this is how, kind of numerical methods tries to tackle these problems using these three kind of approaches. First one is called bracketing, and there's multiple methods under bracketing. We have a graphical approach, which basically you graph it and you try to approximate the root using the graph. And we also have methods that are open. We'll get into the details of all those as we move on. In today's lecture, specifically, we're going to cover two bracketing methods, bisection and false position. And we're going to kind of brush on what's graphical in a kind of a simple equation and show you what that is. And then in the next lectures, which are next week, we'll cover all of these open methods, which are fixed point iteration, Newton-Raphson, secant, and modified secant. All right, so to start, we're going to look at the graphical approach. Basically, you have a plot, you plot the function, you can see, an estimate of where is the root. So in a way, this is not the best way of finding the root because it won't be the most accurate because it depends on the resolution of the image that you have, the resolution of the graph, what are the splits between each unit here. So here we're jumping by 4s, right? We don't know exactly, the decimal places here. So sometimes you cannot get an accurate value using a graph. So what we use these for is basically to estimate where is a root and then apply a numerical method using an initial guess. So in an exam, I can give you a graph with a function, and then you look at the graph and you find where is the root. You can estimate it by looking at the graph. And using that information, you can come up with initial guesses that you can use in the numerical methods. So that's how we're going to use graphs in general in this course. So we're going to do a quick example here on this PowerPoint where basically we have a bungee jumping kind of system. So bungee jumpers you tie your feet and you jump and then kind of bounces when you jump. So there was a medical study that found that your chances of sustaining a significant vertebrae injury increases significantly if the free fall velocity exceeds 36 meters per second after 4 seconds of free fall. So if you fall and after 4 seconds, your speed is faster than 36 meters per second, you're at a risk of hurting your neck. Okay, and that could result in serious injury, or you can get handicapped and so on. So if you were a company running a bungee jumping business, you would want to know exactly what policy I should follow to minimize the injury of anyone following or doing the practice that you have, which is bungee jumping. So what we're going to try to do is solve for what is the mass of the bungee jumper, given the information of the drag coefficient, the velocity, the time, and the gravity, acceleration due to gravity, 9.81. What is the mass that would cause someone to reach this velocity after 4 seconds of falling? So in the previous lecture, we looked at this expression, which was the solution to kind of that differential equation that we had, right, for someone who's falling from the sky, right, with a parachute or, just a free falling person. So we have this expression. It has the velocity. it has gravity, it has the mass, it has the coefficient, the Drake coefficient, and it has time. How do you think we can use this expression to find, a way so that we could find the root, you can say, where the root would be the mass when the velocity is 36 meters per second? How do you think we can use this expression? So if I find the m where the velocity is 36, then basically the left side of this equation and the right side would be equal, right? So if I move this velocity to the right side, then I have a function as a function of m, and where that function equals 0, the mass would give us a velocity of 36 meters per second. Okay, so then I rearrange the function, I move the velocity to the side, and I call this a new function f, and it's a function of the mass. And then I plot this using all of the parameters that we have here. So we plot the graph, we can see f of m on the y-axis, the mass on the x-axis, and we can see the function here. This is the curve, and this is where the function equals 0, this line here. So you can see that that's the root, and approximately you can say that the value is 145 using this graph, right? How can we check if this value is actually somewhat true to the case that we have?
The mass here was supposed to give us 0.
Right, so we plug it back into the equation and we check what we get. And as you can see here, if I plug in 145, I get 0.0456, which is close to 0. If I check the velocity with this mass, I get 36 meters, 0.0456, which exceeds 36 meters, right? So in a way, this graphical approach works, but it does not give us the exact answer, right? In any case, in an engineering problem, if we had something like this, we would probably not use the exact answer in the policy, but have a buffer, right? Maybe 10%, 5% buffer to make sure no one will reach this velocity when they fall after 4 seconds. All right, so this brings us to kind of starting the bracketing methods. And the bracketing methods always require 2 points to kind of be initiated. So we can't start them with one initial guess, and it's not really a guess in the bracketing methods. It's 2 points that bracket the root, meaning that they're around the root, okay? So in this case, we would have a lower bound value and an upper bound value. So the lower bound, right, would be something that's below the root. So you can see here, f of xl, that's below the root, right? So it's a negative value. We're looking at the y-axis. And then we would have another one above. So f of xl could be either this point or this point. F of xu, which is an upper bound, could be either this one or this one or this one. Not all three, okay? We only need one xl and we only need one xu. All right, so xu is upper bound x, and then xl is lower bound x. So to make sure that these values are actually bracketing my root, right, we can check through a calculation. If I multiply f of xl by f of xu, would I get a positive or a negative number? Negative number, right? Because they're on opposite sides. One of them is negative, one of them is positive. I multiply them, I get a negative number. So this condition has to apply, right? When I multiply f of xl and f of xu, I should get less than 0 every time. So if you have this type of question on an exam or a quiz, when you set those 2 points, you want to make sure they're on opposite sides, okay, of the root. You don't want them on the same side because then the algorithm that you are going to apply might not work, okay? It's not the correct approach, okay? So don't do it, basically. All right, so some of the conditions, when we're saying we're bracketing, 2 sections, sometimes if I apply, if I say XL and XU are on the same side, it could be that there are no roots, okay? or there could be an even number of roots. Again, this is not always set in stone, right? There are exceptions to these, but in general, if these bounds were on the same side, it's either you have no roots or an even number of roots, okay? Especially with kind of polynomials. If I have them on opposite sides, it's either I have one root or an odd number of roots. And obviously, you don't want to have a system like this, because if I bracket 3 different roots with 2 points, then my ending result could be either one of these 3. I won't be able to find all 3, right? The algorithm will be applied, and I might just find one of them, and then it will stop. All right? Again, we have here some exceptions to these rules that, even though I'm on the opposite side, I have even numbers. Again, some things to take into account. Anyway, so if I have a function that has many roots, right? So this is a function here that has many roots. Then one way to find out every single root is to write an algorithm that will search through my graph, okay, or through that function. And when I'm searching, right, what is the kind of key parameter here that will indicate I have crossed the root? Change in sign, right? So if I was kind of going through the function, I'm getting positive, 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 suddenly it goes negative. Okay, I crossed the x-axis. Therefore, probably there's a root there. So then that point and the next point would be my bracketing points, okay? When we're doing this search, kind of incremental search, we have to specify an incremental length. How large is my step size when I'm jumping from step to step to find this change in sign? So we could have option A, which is, quite large, and in this case is bracketing, 1, 2, 3 roots, or we can have option B, which is a lot smaller, right? And it obviously in this case is not bracketing many roots except for 1. What do you think is the effect of decreasing the size of this incremental length in the search? It becomes slower, right? Because I'm taking smaller steps. It's going to take a long time to scan through kind of that whole zone that I want to investigate. All right. So the smaller the step size, the more time it's going to require. In any case, even if you take that small step size that I just showed you, you could still potentially miss a root. Okay. So in this graph right here, I'm kind of zooming into this section. We get this graph. I zoom in further to this section. You can see, in fact, that there are actually 2 roots also here, right? And I'm looking at the scale, right? 4.2, 4.25, 4.3. In a way, this is telling me maybe I got to pick an incremental length size of 0.1 maybe to make sure I don't miss any of those roots that are occurring in my kind of function here. Again, this is kind of outside of what we're going to do in this course, but if you ever work on searching for roots, then you want to follow something like this. All right. So we're going to get started with the first, I guess, method. So here we have the procedure, right? This is an algorithm. So this is the procedure for finding the root using the bisection method, which is a bracketing method requiring at least, or for sure, 2 points to start this whole algorithm as we mentioned earlier. So assuming we have some type of function f of x, we want to initially find those 2 kind of bracketing points, all right? So xl, lower bound, xu, upper bound, such that they bound the root of interest, and check that if we multiply f of xl by f of xu, we get less than 0. After that, we would estimate the root. So in the bisection method, it's super simple. You basically take the midpoint between those 2 points. How do you find the midpoint? You add xl and xu together, divide by 2, and you have the midpoint, okay, or the average between 2 points. So in this case, we represent it with a variable called xr, and this is basically the estimated root, okay? So r is for the root. If this estimated root, right, is basically found to be not the root, then we need to basically update our 2 points that are bracketing the roots to move on to the next step, and repeat this process until you get to the root. So to update the boundaries, we need to check, where does XR lie? Is it on the lower side or the upper side? To do that simple calculation, you do f of xl by f of xr. If you get less than 0, it means they are on opposite sides. XL and XR are on opposite sides. So that means XL can remain the same, but X upper is going to be my new XR. All right, so we update X upper to be XR given this condition. If this condition is not true, then we check another condition, which is f of XL times f of XR is greater than 0. If it's greater than 0, it means they are on the same side. Therefore, I would update my lower bound, XL, to be XR. So that's what we see here. Update XL to be XR, and then XU, the upper bound, remains the same, does not change. If you do this multiplication and you get 0, it means what? Right, so XR would be the root in this case. All right, if we're updating the bounds and then we move on to the second iteration, starting from the second iteration, when you calculate the new estimated root, XR, then we can start using this calculation here to find the percent relative error for the given process or iteration steps that we are doing. We check these percent relative errors compared to some type of tolerance, and if it's lower than the tolerance, we stop. If it's not lower than the tolerance, then we go back to step 2, which is calculating a new estimated root. All right, so that's the full procedure. I'll do an example now, following that same equation that we derived in the problem earlier that we basically solved using the graphical approach. All right, so now we're going to do the bisection method on this equation, and we're going to have an initial guess of 50 and 200. So my lower bound is going to be 50, my upper bound is going to be 200, and I'm trying to find that mass that will give me 36 meters per second when the time equals 4 when someone is bungee jumping. All right, so let's draw a board here. All right, so this is going to be the bisection method example. From slide 14. All right, so recall if I had some type of graph for this function here, like this, kind of looked like that from the earlier graph that we graphed. And we would have, x upper, remember this was around 145, so x upper would be somewhere around here, right? So this would be 200, and my x lower would be 50 around here somewhere. All right, so again, this would be XL and this would be XU, because you can see here that this is above the 0, so upper bound. And this value here would be what? F of XU, right? So this would be F of XU. And then down here for the 50, this point here would be F of XL. All right, so from the problem, we said it was already defined that XL is 50 and XU is 200. Just for your knowledge, the true root, is not 145, it's around 142.74, just as background information. All right, so now we're going to apply the bisection method to find the root using these two kind of points. And in every iteration, what we're going to do is start off by solving for the estimated root. All right, so here we have, let's say this is my first iteration. All right, so we're going to say XR is equal to XL plus XU divided by 2. So this is going to be, we have the lower first, so 50, plus the upper, which is 200, divided by 2, gives me what? 125. All right, so that's the first iteration's estimate of the root, simply taking the middle point. All right, so now we want to update the bounds because obviously this is not the root, okay? But we still don't know. And in a program, when it's first doing the first iteration, it still doesn't know what is my percent relative error. So it will continue typically until a condition is met where the percent relative error is small. All right. So we want to update, right? Update the bounds. And in this case, how do we update the bound? Right, so what the thing we need to check is f of xl, right, multiplied by f of xr, and see what we get. Is it a positive number? Is it a negative number? Is it equal to 0? So we plug in here, fl is 50, so we do f of 50 multiplied by f of 125. And the function we're using here is that function f of n, all right, from the PowerPoint that we saw earlier. So we plug in the numbers, we do the math, we get 1.87. So this is greater than 0. So what should we do in this case if it's greater than 0? So if it's greater than 0, it means the lower XL and XR are on the same side, right? So that means I want to update my lower to be this new XR because the upper is on the other side and it should not be changed. So XL is now going to be equal to XR, and then XU is going to remain. Sure, yeah. So we have 200 here, and we have 50 here, and in this root here, it's around 142, right? So this value of F125 or XR 125 is probably going to be somewhere here. Okay, and if I go down like that, so this is XR, say 1, this would be on this side. So that means it's on the same side of f of xl. All right, so this is f of xr. I multiply the two negatives, I get a positive, right? 1.87. All right, so now we can move to the second iteration, right? Because we cannot calculate any errors because we don't have anything to compare with. So let's go to 2 and redo this process and calculate xr by doing xl plus xu divided by 2. So in this case, we have now 125, right, plus 200 divided by 2 gives us 162.5. So now instead of being on the left side, now we obviously are on the right side of the root because we know what the root is, but when you're running this in a program, it doesn't know what the root is, okay? So we always have to check, all right, let me update my bounds and see what value do I get. Before you update your bound, you can also check what is the relative, right? Percent relative error, because we have right now an approximation of the root, right? So in this case, we can calculate also, we can check, let's say check percent relative error, which is this symbol, and we can do the absolute values. And in here, this is equal to the new XR minus the old XR divided by what? The new XR times 100%. So in this case, the new is 162.5. The old is what? 125. Divide by 162.5 times 100%, and we get a value of 23.08%. All right, so this is the absolute from the second iteration. So now we continue. Let's update my bounds. So let's update. Used purple up here. Yeah, we can use purple. So update bound. Yes. XR. Yeah, right here. This is the first. This is XR1. You can say from the first iteration. So we took the middle point. Okay, we took 50 and 200. We took the middle point. It came up here. Okay. What else do you need to know? Oh, that's it. All right. So now we updated. This is the new lower, right? So this is the upper. So we took the midpoint again, and then it ended up being a point somewhere here on this side. So this would be, XR 2, second iteration. Okay, and then after that, now we're gonna update the bounds and then move from there. All right. So to update the bounds, we're gonna check f of xl multiplied by f of xr. And in this case, the lower bound is 125, right? And the XR is 162.5. You do the math, you find that this is negative 0.147, which is less than 0, less than 0. So therefore, what they're on opposite sides, right? So then you don't want to change XL in this case because it's already on an opposite side of XR. So XL remains as XL, which is 125, and then the X upper is going to be now equal to XR, which is 162.5. So now we can move to the second, or sorry, the third iteration in this case. So the third iteration, all right. In the third iteration, we do the calculation again. XR equals X upper or lower plus upper divided by 2. And in this case, it's 125 plus 162.5 divided by 2. And we get a value of 143.75. All right. Now we can estimate again, what is my percent relative error. We do the math. Again, I'm not going to do the full equation again, but you get 13.04%. So one important thing to note for the bracketing methods, it always converges. Okay, no matter what, it will get to the root. As long as there's only one root in there and not multiple roots, it will get to the root that you're looking for. Okay, so again, you update the bounds. All right, let's just do kind of a quick update bound. All right, and then you move on to the next step. So you continue this, right? And on the PowerPoint here, I have the results. Continue this. So typically you want to do this either in Excel or you want to do it in MATLAB itself because it's a lot quicker. But for the sake of the course, we also have to do it by hand, okay? So that we can evaluate that you understand what you're doing, okay? So here we have the lower bounds, the upper bounds for every iteration up to 8th iteration. We have the root, the estimated root in each one. And then we have the percent relative error. And as you can see, it's decreasing, right? Gradually decreasing. While the true percent relative error, so this is comparing the values we get of XR to the actual true root, does not necessarily have to decrease constantly. At this point, like second iteration, we got really close to the root, then we went away, then we came back, and so on. All right. So graphically, these kind of true percent relative error and percent relative error kind of looks like this. All right. So we have the true percent relative error kind of jumping around and then kind of showing convergence, while the percent relative error is converging all the way. All right, so pros, It's super easy. We take the two bounds, right? Find the two bounds. We just take the half point every time. Repeat. It's really easy to do. Always finds the root. We can actually calculate how many iterations are required to get an absolute error. I'll show that in the next slide. In the cons, it's really slow. You know, it can take quite a number of iterations to find the solution. Obviously, we need to know the bounds. So in some cases, you know, you physically might have to graph the plot and look at where are the bounds, or you have to use incremental search to find them. If you have multiple routes, it won't, you know, give you that one route or all of them. It'll just give you one route. It won't solve all three. And also, it doesn't compare the values of f of xl and f of xu to know, okay, this one is actually closer. We should maybe change the other one, right? So again, it's just a simple algorithm and could be modified to be smarter and hence perform better. All right, so how do we find how many iterations do we need to get a certain number of absolute error? The maximum absolute error for the bisection method, okay, is calculated here assuming that one of the boundaries is really close to the actual root, okay? Like if I have a graph here, this is a graph, and this is kind of, you know, my function here. If one of the estimated roots is like right here, and the other one is like right here, okay? So this would be XL, and this would be this is XL, and this is XU naught. So these are kind of the initial estimates, or the boundaries. The distance from this point to this point is what? XU naught minus XL naught. So this is delta X naught, okay? So this here is the maximum absolute error for the root estimation, okay? If I do a single iteration, what happens? It halves this, right? So I'm going to go all the way to this half point, and the maximum absolute error becomes delta X naught divided by 2. If I do another iteration, it's going to halve to here, right? This will be what? This distance compared to all of this? Fourth, right? So delta X naught divided by 4. So essentially, the equation is delta X naught 2 to the n, where n is the number of iterations, okay? And this will give me what? The maximum absolute error. So if I have a desired maximum absolute error, I can plug it in here, right? This is a desired kind of absolute error. I can solve for n to know how many iterations I need to get this in the bisection method. So again, I kind of wrote on this slide, but all the stuff that I just mentioned is on the slide itself. Let me just go back to the slide here, erase these things. All right, so we can see here after one iteration, we have delta X naught divided by 2. Second iteration, delta X naught divided by 4. N number of iterations, delta X naught divided by 2 to the n. All right, so then if I have, again, a desired error, I can solve for n, and to solve for n, you rearrange, and it comes up with these kind of weird-looking equations, but they're just logs, and you can solve them using a calculator or Excel or math. Any questions on the bisection method? All right. So we're going to move on to the next method, which is the false position method. All right, so unlike the bisection method, this is a bit more complex, but not too complicated. Imagine we have a function, this blue line here, this is our line of the function, what we're going to be doing is, again, having an upper bound and a lower bound. Okay. In these 2 points, what we're going to do is we're going to estimate that the function itself is a linear function. All right, so we can see this kind of linear line here between the upper bound and the lower bound. And from that linear line, wherever that crosses the x-axis, that's going to be our estimated root. Okay, so again, it's a simple equation that I'll derive for you guys in a second. But using that equation, we're basically assuming a straight line, and where that straight line between the 2 bounds crosses is the estimated root. So again, just like in the bisection, I have a kind of slide with the procedure. So in this case, you want to find values of xl and xu, where xl or f of xl is less than 0. So here it's more kind of distinct. F of xl needs to be less than 0. In the bisection method, it's not really an issue. As long as they're on opposite ends, it doesn't really matter. All right. F of xu has to be greater than 0. All right. Once you have that, then you can apply this equation, which I'll derive in a second, to find the estimated root. Okay, again, this assumes a straight line and finds this estimated root. Then, similar to what we did before, we want to update the bounds. So then we want to check the values of f of xr. If f of xr is less than 0, then I update the lower bound. Okay, x upper bound remains the same. If it's greater than 0, then I update the upper bound and the lower bound stays the same. If it's equal to 0, then we found the root and then we stop. Again, starting from the second iteration, we can calculate the percent relative error, check its value compared to some type of tolerance, and then if it's not less than the tolerance, then we repeat. So go back to step 2 and repeat this process. All right, so let's derive this equation. You're not required to know how to derive this equation, but it's, for the sake of learning, where do these equations come from, and understanding how numerical methods kind of develop. All right, so we're going to do the false position here, equation derivation, and this is from slide 20. So let's imagine we have, again, some type of plot here, and we have this kind of curved line. And let's say that this point here is my x upper, and this point here is my x lower. Again, so this would be my fxu, and this would be my fxl. Between these 2 points, I'm going to draw a straight line. All right, so let's try our best straight line here. All right, so that's a straight line. And this here, where it crosses the x-axis, right, would be my estimated root. So this is going to be xr. So to derive the equation, we're going to look at the slope of this straight line. So we're going to have 2 slopes. The first one, all right, m1, is going to be the slope between, we have the points on the 2 ends of the straight line. So we have the lower bound, so xl and f of xl, that's 1 point. And then the other point is xu, which is the upper bound, and f of xu. All right. So from calculus, what is m1 in this case? Right. I'm going to do just the opposite of that, but it's basically the same thing, just flipping the equation. All right. So basically delta u or delta y divided by delta x is the slope, right, for a straight line. And this is basically what we're doing here. All right. The second slope in this case is going to be m2. And m2 is going to be involving this XR point. All right, so we're gonna do slope between XR. What's Y XR? Yeah, what's f of XR?
Which is the
It's 0, right? So this is 0. And then the second point would be, in this case, that we're going to use is xu and f of xu. So just in the same way, now we have, m2. And this is going to be negative f of xu divided by xr minus xu. So what's the relationship between m1 and m2? They're equal, right? So since straight line, it doesn't matter where you take the 2 points, the slope is always equal. So since straight line, m1 equals to m2, and in this case, we can plug in, f of xl minus f of xu divided by xl minus xu equals negative f of xu divided by xr minus xu. Then you can rearrange and basically solve for what, in this case, xr, right? So then xr, after you rearrange, is simply going to be, xu minus f of xu times xl minus xu divided by f of xl minus f of xu. All right, so this is the false position method equation that estimates xr using a straight line between the two dots. Any questions on this derivation? All right, so let's compare the bisection to this method. All right, so we covered that. So false position can be faster than the bisection method, but not necessarily true. So here I have an example where the bisection would be a lot faster than the false position, where we can see that every time I draw a straight line, I'm estimating a new root, but my step change is really small, right? This will take quite a bit of iterations to find this root, which is at the point or the unity point 1. All right, so now we're going to do an example using the false position example, using the same problem that we did before. And then we will also look at some of the results in a graph of when we compare section to what we just did in the false position for the bungee jumper problem. All right, so the bungee jumper problem, going back to this drawboard here. So this is the last thing today, so, we're almost done. All right, false position. Example, slide 22. All right, so we have XL equals 50, X upper equals 200. And in here, we would basically have to do iterations, right? So the first iteration would be solving for XR using the equation that we just derived up here, right? So we have XU minus f of XU times XL minus XU divided by f of XL minus f of XU. So you'd have to solve, obviously, what is f of XU, what is f of XL, and then plug them into the equation to be able to solve for XR. It's not simply finding the half point, right? Like the bisection method, all right? So in here, this is 200 minus 0.860291. So for some of these numbers or equations, expressions, I will write down the numbers, and you can try them out later, right? And see, in fact, that you get these numbers. What we're focusing on is not doing math, right? Simple calculations. What we're focusing on is the actual algorithm to show, how do we perform false position and how do we perform bisection, all right? So that's why I'm not doing all of the math steps in between. All right, so you do this math and you get a value for XR, which is 176.2773. All right. So now in the false position, after the first kind of estimate, I want to check, where does this lie in comparison to my other bounds? Is it in the positive side? Is it in the negative side? So that I can update, right, my bounds. So update bound. So we're going to check, in this case, what is the value of f of xr? And this will give us kind of the conditions that we'll use to apply our decision. So we find that it's a positive value. So in that case, which one do we replace? So we replace suspense XU. All right. So in that case, we have XL is going to remain at 50 and XU is going to become 176.2773 instead of its original 200. All right, so that's the first iteration done. So now we move to the second iteration. All right, so in the second iteration, we apply the same equation that we saw above. So this full XR equation, okay? I'm not going to repeat it again because of, there's no reason to redo a whole bunch of writing for no reason. But it's basically the same equation above. You do the math, you find 162.3828. All right. Now we can check what the error, right? So now we can do the percent relative error. In this case, it's 8.56%. What's the next step? F of XR, which is basically updating the bounds. So then we do F of XR, and we find that this is equal to 0.357509. Again, positive number, so replace X of lower or upper? U, right? Again, it's a positive number, so we want to replace the upper bound, and therefore we now have still XL at 50, and XU is now 162.3828. So this is the common characteristic of the false position method. One of the points usually is just fixed and not moving, while the other points just keep shifting towards the root. All right, so now we do a third iteration. All right, you do XR, you find that it's 154.2446. You check the relative error. Again, it should be decreasing unless you did something wrong, okay? So always in these bracketing methods, okay, we're always converging, all right? It does not diverge. So if I ask you on an exam, comment on the convergence of the bracketing methods, you should say they always converge, okay? Don't say sometimes they converge. because it's not sometimes. All right. So again, you can check f of xr. You find that it's 0.219 positive and so on and continue. So looking on here in the PowerPoint, I think I have do I have further points? I'm not sure if I do. Let me see. So I only have the graph of the true percent relative error. Okay. And what we're doing here is we're comparing the false position to the bisection method. And they're both converging, quite closely at the same rate in this problem, given the initial conditions that we have, so the 50 and the 200. The bisection actually gets a bit faster, to that true point compared to the false position, but relatively it's quite the same. All right. So that ends our lecture for today. We covered, the two bracketing methods, the bisection, the false position. We looked at kind of the graphical approach, the simple approach of solving for the root. I hope now you understand what's a root. And in the next lecture, we're going to look at the open methods.